Hey everyone! Welcome to June's Rock Game Dev Workshop. So glad you could join us. In case this is your first time tuning into a Rock Game Dev Workshop, I'm Sam, Rock Game Dev's Workshop Coordinator. Rock Game Dev is an organization dedicated to fostering a community of game creators in Rochester, New York. Our mission is to provide a local platform for game creators at beginner, amateur, and professional levels to learn, share, and collaborate in all aspects of building games. If you want more info, head on over to rockgamedev.com. And if you've gotten an idea for a workshop you'd like to give or a workshop you'd like to see, please let me know. You can find me at Sam_Camerata on Discord and Sam Catamaran on Twitter. Which then brings us to tonight's workshop, Prototype Faster with Event-Driven Architecture. Our speaker, Noah Ratcliff, is the lead developer at Aesthetician Labs and has been making games for nearly a decade. Cutting their teeth on game jams, Noah has developed workflows and tools that have allowed Aesthetician Labs to build and test 60 plus hyper-casual games in the last year and a half. Much of this speed is due to the event-based approach to game architecture. Tonight's talk will explore event-driven programming for flexible game architecture and how it can be leveraged for rapid prototyping. Examples will be given in Unity and C#, but the fundamentals should be applicable in any language or engine. Some level of experience with game programming is expected. Feel free to drop any questions you have in chat as we go, and with that, I'll hand it over to you, Noah.
All right, I'll hop in. I made a slight change since I sent that text to Sam. It shouldn't say expected, recommended is fine. Don't worry if you're still pretty fresh, still pretty green, that's okay. Just wanted to set the expectations right. So yeah, this is definitely, it's not gonna be a 101, but it shouldn't hopefully be too complicated either. Only one way to find out. So with that, let me just get the last few things set up here. Oh, that's not what I want. All right, we'll roll with this. Okay, so prototyping faster with event-based architecture. I'm gonna have some example code in this slide deck. And so as I go over that, if anybody wants to kind of pour over that with a little bit more detail, I have a GitHub repository here that has the example code as well as the demo that we're gonna go through. So if you see something and you don't get a chance to actually look at it, you maybe want to go back and revisit something to that effect, please feel free to go ahead and go into that repo and follow along or look ahead. I don't really mind. Yeah, whatever floats your boat, but that's there for you. So let's get started. Yeah, so I'm Noah. I am an RIT Game Design and Development alumni. I have 8+ years experience making games and 3+ years as a co-founder and lead developer at Aesthetician Labs. I have 60+ hyper-casual prototypes tested in the last year and a half, and I would say I'm a jam fan. I used to do a lot of Ludum Dare. I've done the keynote for Ludum Dare, and I think I went 5 years without missing one of them. And I am a cloud admirer. So this talk is going to cover primarily event-based design patterns, programming patterns, and mostly the observer pattern, and then common problems that event-based architecture can solve, as well as about how event-based architecture helps with rapid prototyping. So how can we apply the observer pattern and event-based programming to rapid prototyping, right? And then we'll go over some pitfalls and gotchas as well for the pattern. Some experience with game programming is recommended, like I said, although not a requirement. Again, everyone is welcome to follow along to the best of their ability. And of course, please feel free to ask questions as we go. I have the chat pulled up here, and then I've got Sam behind me to yell at me if I don't catch a question. So please feel free to just fire away in the chat. We'll try to grab them as they come up, but I might, have to circle back if I move on and a question comes up with the stream delay. So examples will be given in C# using Unity, but the concept should apply anywhere, and I've really tried to tailor this talk to be a little bit more agnostic. And the observer pattern is really born out of C-based, I think C++ was the original example given for the observer pattern. So these concepts do apply outside of just C#. So don't get too worried that this isn't going to apply to what you're doing. It should apply everywhere. We will be exploring some Unity specifics just because that's a huge portion of people making games, and there are some interesting things to explore there. But I'll try to keep that short. So before we get into what is event-based architecture, let's talk about what isn't event-based architecture. So W3S Design is a website that provides a good description and summary of the observer pattern, as well as many other Gang of Four patterns, which we'll get into that in a second. But they define, or they say that in a flexible way to define a one-to-many dependency between objects is to define one object that implements updating the state of dependent objects. So that means the subject must know how to update the state of many different objects. And that's a very familiar problem in game development, where you have one subject that updates a bunch of dependent systems, right? And so you could have, the UI and then the physics and everything being updated, and kind of just a chain of update calls, right? And then so it has to know the particulars of every single dependency, right? So it has to engage with these different interfaces, right? This is a tweet I sent when we were just coming out of the tail end of working on our game Crazy Plates. And I think this is a highly relatable sentiment in game development, especially in Unity, but the just totally tangled mess game manager that's just got everything thrown into it. It's got, everything kind of all roads lead to Rome type situation where everybody touches game manager at some point, or game manager touches everything at some point, So this is I think everybody who's worked on games in some capacity has encountered this at some point, where it's just a mess, especially when you finish projects. Sometimes you're just like, okay, I just have to get this stuff working. I'll just start throwing it into game manager. As an example, this is this is the entire Crazy Plates game manager file, all 1,279 lines of it, in this one very skinny screenshot. I had to add some highlight behind it because it was nearly invisible. Unreal sometimes literally looks like that. Yeah, exactly. So it's totally common. I think so many people run into this type of problem where everything just ends up getting thrown into like one class, and then it's a mess to work on, right? Often, in projects you'll see an overuse of singletons. So it's kind of a teach a man to fish type of problem, or rather, it's more of a when all you have is a hammer, everything is a nail type of problem, right? Singletons are really powerful, but I think especially in game development, again, when you're like, okay, well, we'll only ever have one player, so let's just make the player a singleton. Okay, well, there's only ever going to be one game manager, so clearly game manager needs to be a singleton. And maybe in some cases that decision is right, but you can quickly see how that stacks. Okay, there's only ever going to be one ball in our Pong game, so we don't need to worry about any other ones. The ball will just be a singleton. Well, and suddenly you have two, and things get really messy. Most of the game logic in just a couple of classes, super tightly coupled systems, like I said, going back to the phone poll, and just a tangled mess of dependencies. It's really hard to work on. When you want to add a feature, it breaks something that seems completely unrelated. This is a common problem in game development. W3S Design summarizes this problem as it commits or tightly couples the subject to a particular dependent objects and makes it impossible to change the objects independently from the subject. It stops the subject from being reusable and makes the subject hard to test. So tightly coupled objects are hard to implement, change, test, and reuse because they depend on many different objects. And that's really the key here, is that when we're talking about rapid prototyping, it's really important to be able to quickly implement, change, test, and reuse systems. All 4 of those are really important principles of rapid prototyping, is that you make your systems in a way that they can be quickly changed, quickly implemented, quickly tested, and quickly reused. So that's the core problem that tight coupling creates. So the solution, well, interestingly enough, in this picture, we actually have maybe a little bit of the solution, and that's the siren here at the top. And in fact, somebody in the replies to this tweet pointed it out. The siren is for broadcasting events to subsystems, at least some level of decoupling. Not all hope is lost. And they're right. That's exactly, I mean, this is a pretty good representation of how the event pattern works out to work, is it basically is a broadcast notification to say, hey, something has happened, and then all the other systems that care about that particular event can receive that event and then take action on it. So that, in a very abstract, is the observer pattern, but we can drill into more, a better definition. In fact, V3S has us covered. The observer pattern basically defines a subject and observer, or subject and observer objects, so that when a subject changes state, all registered observers are notified and updated automatically. So it lets one piece of code announce that something interesting happened without actually caring who receives the notification. And that's the summary. I think that's put a little bit more into English by Robert Nystrom, the author of Game Programming Patterns, which is an incredible book and is free and available. It's in the references for this slide deck, which you'll have a link to. It's a really invaluable resource, but that's how he describes it. It's a piece of code that announces that something interesting happened without actually caring who receives the notification. So again, just reiterating, it allows a system to notify an arbitrary number of other systems without needing to be aware of them. And in the observer pattern, often they call that the system that sends the notification a subject, and the systems that receive the notification observers. So the observers literally observe the subject state, but from a decoupled perspective. So like I said, this was originally defined by the Gang of Four. If you've ever taken any programming classes, you've heard of the Gang of Four. If you've ever done any research, I think really quickly you run into these folk and this book. What it does is it decouples the subject from observers in one-to-many relationships. So when you have a one system and many kind of dependencies on that system or piece of information, this helps create a decoupling effect so that the system that has the important information or generates the important information does not have to care about the particularities of the systems that depend on that information. And observers don't even need to check the state of the subject. They just wait for the event. So if the subject doesn't even exist in the runtime, let's say, if it's not even present or it's not in the scene in Unity, right? The observers don't care. They'll just sit by idly and wait for something to happen. So from the subject's perspective, it's a completely fire and forget process. It just says, hey, I did this, and then moves on, right? It just shouts it out into the world. And from the observer's perspective, they just hang back and wait until something happens. Okay, I'm listening, and when I receive the notification, I'll do something. So the classic implementation of the observer pattern is basically that the observer is implemented as a simple interface that provides an onNotify method. So basically, it's a method that can be called with an event, an arbitrary event, right? That also could be an interface, or an arbitrary piece of data. You could just make that an object, whatever. And then the subject holds a list of observers and provides an API for adding and removing observers, right? So the subject keeps track of the observers that are registered to it, and then when it comes time to notify of an event, it notifies and walks through that list of observers and calls onNotify with the event data for each of them. So instead of individually calling UI.updateText and player update score, so on and so forth, they just say observer.onNotify. So it's a more abstract system. So if we take an example of maybe like a player getting hurt, right? So we have a player that is a subject that notifies its observers when it's hurt, right? So it has health, it has a hit method that subtracts damage from the health, and then notifies its observers. So it says notify, and it sends its player hurt event, which contains the amount of damage that the player took. The player health UI can be an observer that in its constructor starts watching the player and says, okay, hey, I'm going to watch for your event, your player hurt event. And then onNotify receives that player hurt event and then updates the UI. So when you take damage, it can decrement the health bar. In more modern cases, we have like constructs and languages now that kind of supersede the original implementation, or actually just build on top of it, really. In C# we have the events system and events API, and in Unity we have Unity events. And both of them have their strengths and weaknesses, which we'll talk about way in the end. But most modern languages have some form of event system now, which is primarily based on the original definition of the observer pattern, that walking through a list of observers and invoking some kind of method. C# has these events that can be implemented in kind of a couple different ways. You see the first one here is called action, and then we provide a float type parameter for that action, and we invoke that action providing the damage, or we call it just directly as if it were a method. And so the way it works in C# is it actually kind of takes it as a anonymous method in a sense. The player health UI then subscribes by just adding its method to the onHurt event as a callback method, right? And so it will be called in the list basically exactly the same way as walking down that list and invoking it. You can also use anonymous functions. And so in C#, right, or languages with anonymous functions, you can say, I'm just going to add this kind of inline function here that will handle this thing. And so you don't even have to have a function definition in your class or static method or whatever, right? So the other way that you can do this, if you don't use an action, or there's another one that for some reason is evading my, there's a second interface for this, but there's also delegates, which provide maybe a more bespoke way of defining this. And actually, actions are just delegates under the hood. But basically, you can say, okay, I have a delegate type, which is onHurt delegate. And so I expect a function that takes a float, and that's what I'm defining as an onHurt delegate. And then you create a public event onHurt delegate. And really, the event keyword only says that this thing can only be invoked from the class that it's defined in, so somebody else can't get a reference to it and invoke it, because that would break, that creates some kind of unsafe conditions. So here, the onHurt delegate and action with the float and the braces is pretty much this exact same definition, just two different ways to get to the same thing. I generally tend to lean towards using actions just because it's easier to just quickly throw together. But you can, of course, just define your delegates more explicitly here. And you can also define return types and that kind of thing with delegates. And like I said, there's func, I think, is the other one, which allows for return types. Also, if you have a huge list of parameters, then a delegate might be better, because it could just be annoying to define as an action. So it works very similar, though, like I said, to the original implementation. And Unity has a similar thing that basically is built out of the C# events API. The Unity event, basically you can define just a generic Unity event that has no parameters, and that's fine. That'll just be a standard callback. Or you can define a Unity event with parameters, but an interesting quirk is that you actually kind of need to define it as its own type. So you have to say, you know, we have a class player hurt event, right? That is extending the Unity event with the parameter, the float parameter. And the reason that we have to do that is so that it can be serialized to appear in the inspector, because Unity provides kind of a custom interface to add callbacks in the inspector, which is really cool. And so that's one of the big advantages of Unity events system, right? Is that you actually can kind of have a no-code event system. So just a little quirk that you have to do that. It might look complicated, but it's really just you have to have an empty definition for the type that inherits from the base type to be serialized, because the Unity serialization class or serialization system doesn't handle the generic types very well that their events rely on. But again, same thing, subtract damage from health, notify observers. Now, interestingly, you do have to call invoke. Unity doesn't implement the direct invocation here, so you do have to call invoke. Often I'll use invoke for both because then it's easier to switch out. So if I switch from a C# event to a Unity event, all my calls don't break, right? So I can quickly just switch out because both do provide the invoke API. But it's the exact same under the hood, whether you call either of these. And then from the perspective of our player health UI, this unfortunately is a situation where you can't just use the plus equals like in C#. You call add listener and then provide your method. Or you could do an anonymous function again here. It works pretty much the same way. You just call add listener. So to reiterate, this helps because it allows you to decouple systems and make them more modular. So they're easier to reuse, test, and change. And again, those are core principles of rapid prototyping, is to don't waste your time writing code that will inevitably tie somebody up in the future or tie yourself up in the future. Try to write systems, you know, within reason. Obviously, don't waste your time over optimizing your architecture, because you might have to delete all of it and start over. But you want to write systems that can be reused, that are testable, and are easy to change, right? Especially reuse. You can take things out of a project if you give up on it, right? And then move it into the next one. Say, okay, well, this, you know, the way that we handled updating the UI, right, from watching these values, like we can take that whole system and put it into another game, especially if we build it with just a little bit of modularity and decoupling in mind, right? And also, separation of concerns is a huge kind of keyword that you hear. Again, if you ever take any programming courses, and separation of concerns really just means that systems that don't have anything to do with each other don't do anything with each other, right? So if I have a game manager that really should just handle the game state. It should know about the state of the game at a high level and then notify everybody else. It does not need to know about what the UI is doing right now. It does not need to know about what the player is doing right now. And the player may want to know what the game state is, but it doesn't care about the particulars of how that's implemented, and the game manager shouldn't care about how the player updates relative to the game state. So that's the separation of concerns that we create there. It also reduces dependencies and missing/null references, so you don't have to assign a bunch of things to each other, again, because if everybody isn't dependent on each other, then you don't have to manage a lot of assignments, especially in the Unity editor. It's a common, again, thing to drag a prefab into a scene, hit run, and then you get 5 errors in the console that are like, oh, well, I don't have a reference to this, I don't have a reference to this, so on and so forth. And especially if you work with non-technical people, that can be really scary. They're like, oh no, I broke the game, and then they come to you, and as a developer, that's taking some of your time to handle something that, if with a little bit of planning, you maybe could have handled yourself and solved that problem ahead of time. So it helps reduce those problems. And they don't even need to know about the source of a notification. It could come from multiple sources. So through that decoupling, you can it's pluggable on both ends, right? The notification itself can come from any arbitrary source because the listener, the observer, doesn't care, and the subject doesn't care about who's listening. So it's perfect, right? And it's easier to add juice because now you have a system, you already have a system for notifications, And so you can receive those notifications and then react in the game accordingly, right? And we'll get into more specifics, but it's a lot easier to just quickly throw in particle effects, for example, in response to something happening in the game, because you already have a notification that that thing happened, right? It's easier to animate UI when the game starts, have the UI not shown and then it has like a nice animation in when the game starts, because the UI can just grab the game state out of the ether, basically, when it changes and then respond accordingly. And there's often no code that has to be written for that kind of stuff in Unity. And if, depending on what you're using, it's very minimal code that has to be written in that case, right? So, for example, UI can update a counter when the player collects a coin, right? And so we have a coin collected event emitted from the player. The effect system can play a particle effect when the player collects a coin, right? Achievement system can sit in the background and unlock an achievement when the player collects their 1,000th or 100th coin, right? So increments, it keeps counting until the player's unlocked their 100th, and then it unlocks some kind of achievement. And especially in input, this is where you actually see the observer pattern used the most, and often you have been using the observer pattern, you just haven't noticed, especially if you're using Unity, especially with either their new input system or Rewired or any of the other kind of input improvement systems that they have. So when the player presses space, we emit some kind of maybe like jump event, right? We convert that space key into a jump event, and then the player will jump when there's a jump event. The input system emits the jump event when space is pressed. But then we can make the hero jump when the player presses a button in the UI, because that UI button could emit the exact same event. Again, we don't care about where it came from. We can make them jump when the player presses a button on their gamepad, or when the AI decides to jump. And then we can play a particle effect when the hero jumps, all from the exact same event, right? Again, it's on both sides. We don't care about the subject or the observer if we design our architecture correctly. So, walking through some of these examples. So if we update the UI when the player collects a coin. So the traditional way that people might do this is they would say, well, we have a player and they have their coins, right? And that's defined here as a property, and it's, they have 30 coins, right? And then when we call collect coin, we increment coins, and then over somewhere else we have a coin counter UI that's just hanging out in every frame, checking the reference it has to the player, and just updating its text every time that every frame, right? So it goes and it gets the number of coins, converts that to a string, and updates the text. And maybe if we were being a little bit more conservative and we optimized a little bit, we would say, well, let's just check if the coin value changed from what we currently are showing. So we keep an internal displayed value or something, right? And so then we check, is that different from what the player's coin value is? If so, update our text. Okay, we've improved it a little bit, but we're still doing that comparison every frame, and we've got one more thing in update, right? So with the observer pattern, we can define an action on coin collected on the player, right? And then in collect coin, we invoke that on coin collected. And from the UI's perspective, the difference is that when we first are initializing, we say, okay, we're going to listen to that coin collected event, right? And then we're going to receive a callback to our coin collected method, and then we're going to update the text. So only when the player collects a coin do we actually change the displayed value. And now if we were being even more kind of perfect to the observer pattern, what we would actually have is like a coin value changed, and so every time the coin value changed, that would be invoked. But this is just an example, right? Now, the one problem here, though, is that we still have a dependency. We still have to have the player to be able to register this event. And we'll get to that. We'll get to that in just a minute, but just keep that in mind that we do still maintain a dependency, but we've at least decoupled a little bit in terms of performance. We're no longer checking every frame. We're not updating every frame. So we can do some other stuff when the player collects a coin with this kind of system. So we can say coin collected effects. We have our particle system, we have our player. Again, register our callback, play the effect when the coin is collected. From the achievement perspective, we keep track of how many coins we've collected just globally, right? And again, the player doesn't have to care about that. The player doesn't have to know about the achievement progress, the achievement system handles that. And so when a coin is collected, we increment our internal value, and then when we're over 100, we unlock the achievement, right, or whatever. So you can see, again, this is like where I'm trying to plant the seed that this is how you lay the groundwork for easily expandable infrastructure really quickly, right? You can quickly add features layered on top of the existing system that you already have if you start thinking about events and where they fit into your infrastructure or your architecture from the start. So now the original observer pattern was defined by the Gang of Four in their book in like the 90s or whatever. Don't quote me on that. I'm actually really bad about that, their specific situation. Everything these days is largely derivative. So the original pattern is very object-oriented, though. It came from the heyday of object-oriented programming. And modern languages and frameworks usually have some kind of function-based event system like we saw. So we have the C# events and Unity events. But common implementations involve the observer having some kind of reference to the subject and a list of observers being stored in the subject. And that's coupling, right? You still have, the observer has to know about the subject still, right? To be able to observe. So what if we made the event the subject rather than the source of the event, right? So if we say, in the way that I usually implement this, if we say that our events or notifications are a type or a class, right? We could use anything like a string or an enum or whatever, but types help simplify the data access. Like I said, it becomes the subject. So this separates the subject from the source of the notification. So the notification still comes from the player and it's packed with the data, for example, the number of coins, but the way that you listen is by reference to the event, not by reference to the source. So in this case, I usually set up some kind of event dispatcher, singleton, or static class, and that stores a dictionary of event types to listener methods. So similar to our list of observers, we store event type mapped to event like method lists, right? So same as like in C# you would have your action, it's event to action. And then it provides an API for adding and removing listener methods for events and handles dispatching or notifying listeners of events. So, that's why we call it event dispatcher. And I'm going to move from there's a lot of different language that I'm going to use throughout this talk, and it's always going to be kind of on top of each other. But basically, we're going to have events being dispatched, and that's pretty much the same as a notification being sent to observers, right? If you have any questions on that point, if you ever feel confused, please let me know, and I'll try to clarify as best I can. So our event dispatcher, like I said, it holds a reference of event type to actions that receive the event. And so you see we have that iEvent interface again. And then we also maintain a map of generic listeners to our type listener. This is a little bit of a quirk of C#. Other languages are similar. It just depends on what you're working with and how rigid their type system is. And we'll get to exactly how that works. You don't have to worry too much about this implementation that much, but I'm just trying to run you through the whole thing. So basically what we do is we provide the add listener and remove listener methods, and what those do is they take as a type argument, they take the type of event we're listening to, and then they expect a callback method that is a action of that receives that type as a parameter. So we can use, this is maybe a little bit confusing, but actions and the methods are kind of the same. When you provide a method as a parameter into a method, it becomes it's encapsulated as an action, and then you could theoretically add additional events to or additional actions to that chain. They're all kind of the same object. So here we say, we take a event parameter and the callback that receives that event. And then we say, we get the type, and then basically what we do is we create an anonymous function that casts the event into the type that we actually expect or that the callback expects, because all of our callbacks, like we saw, are going to be stored as iEvent callbacks, and so these are methods that expect an iEvent type, not a specific type. And we could have all of our listeners expect an iEvent and then just do the cast inside of their event, but that's a little bit messy, right? Or inside of their event handler. That's a little bit messy, and so this just kind of adds an additional layer. We wrap it in one additional call that does the conversion for us real quick. It just casts it, and this is safe enough because we know for a fact, because we're in this, we have a type parameter provided. We know that cast is always going to be valid. And then we store the iEvent version for removal later, and that's what I said. We have this listener lookup, so we have to keep track of that because we want to be able to remove it later. Then we add the listener callback to the event delegate here. So we say we get the action delegate, right, for the type that we have, and we add our callback to that, or it becomes the callback or it becomes the delegate. Because again, like I said, these callbacks can have, the way that they work in C# is you can just start chaining them right out the gate. So like I said, you don't have to worry too much about the particulars of this implementation if you're a little confused or a little bit hazy on it. But of course, please feel free to ask whatever questions you have. So remove listener does the opposite of add listener. It removes the provided listener from the event. So we get the type, we get the method as a callback, and we do kind of the same thing in reverse. We find the iEvent version of the callback, right, in our listener lookup dictionary, and we remove that from the delegates list, right, and then we remove the original callback from our listener lookup dictionary as well. So remember, this converts our typed delegates to our iEvents so that we can get them from our actual generic delegates. So we remove it and then throw an error if we couldn't find it. But the core principle is that we find the generic one, we use that, or we remove that from the delegates list for the specific event type, and then we remove the generic or the specific one from the dictionary. And then finally, much easier, dispatch notifies all listeners for an event. So when we want to make a notification, we call dispatch, we provide the event. It looks up the delegates in the delegates dictionary for that event type. It finds the callback and it invokes it with the event. So it gets the type, uses that to look up any listeners for that type, and then if there are any, it invokes it. And if there aren't, it just silently says, okay, well, I sent it. Again, the thing sending the notification doesn't care if anyone was listening. It just wanted to send it, shout it into the void. So there's a visual example here. We have our player with their coins, and we collect our coins, and I accidentally left a little bit of irrelevant code in there. So ignore old value, but we increment their coins, and then the important thing here is we call event dispatcher.dispatch, and then new coin collected event, and we provide ourselves as source of an event. This is a common pattern, not necessarily to type it so firmly, because again, there is some coupling here, but in C# especially, you'll see their events often, and I believe it's their standard to have provide the source with the event. So you would say like object source, right? And it's just a generic object, and you might already know what it is, and you can maybe do some checks to see what it is if you needed to. In my case, if I absolutely have to, I'll provide it, but I usually try to provide explicitly the data that would be needed so that it's less coupled. So again, coin collected event. Basically we say a player collected a coin, and so it creates that object and then sends it through to our coin counter UI, which is called add listener when it was initializing. And now coin collected is called, and we say, well, text.text equals our sources coins.toString. And so maybe an additional level of decoupling, we could say, I really would probably, in this case, we would use just do coin value, check the change on that. But again, this is just an example. Like, you can dispatch this event, it flows through into the listener, and it could go to many other listeners, right? It doesn't just go to the one. So let's slide on over to real demo in Unity. Now that I've hit you in the face with a bunch of information, fly over here. So here I have a breakout clone. Let me get my notes up. Yep. So here I have a breakout clone, and you see it's it plays mostly just like breakout. I can move my paddle, and I can break blocks, and that's pretty nice. That's pretty cool. Nothing too fancy though. But let's talk about the particulars of how we've implemented some of this stuff. So we have, let's start with the paddle, right? So we have a paddle that, let me zoom this in a little bit for everybody so that we can see. Unfortunately, Writer zooms by window unless I globally change my font settings. So this is what we're going to work with. But we have or zooms by tab rather. So we have a paddle. We'll ignore most of the movement physics stuff, but the paddle listens for a move event and then stops listening for the move event when it's destroyed. This is a Unity specific function that basically says when either the scene is unloaded or the object is destroyed in the scene. This is called right before it goes out, it disappears from the runtime. So we remove the listener so that we don't run into any issues with the listener being called once the player or the paddle is destroyed, which we'll talk about that a little bit more detail in the gotchas in the end. So basically, the core thing, right, is we have we're updating our movement if we're moving, and we do a little bit of physics handling here. But the core thing is, we move with our movement direction, and we clear if we've changed directions, and then we move with our movement direction and a defined move force on the player, right? And then we use that as a force on the rigid body. But the important part here is that the onMove callback. So we've registered our onMove, and so we receive a move event. We look over here in our events. Again, zoom in a little bit for you. So here in our events, we have a move event, and it provides a direction, which is just left or right, -1 or +1, and event action type, which is start or stop, right? So we say, action and direction. So we receive a direction, we convert that to an integer. Like I said, it's either 1 or -1. And then we check, okay, are we starting? So if we're starting, then we say moving is true, and we set our direction. And then if we're stopping and the direction is the same as our move direction, to prevent kind of weird bug where if you had both keys held down, you released one, you might stop or change directions. So we say only stop if it's for our current actual direction, we stop moving. So again, we'd stop moving because we only call update moving if we're moving, which is set here. And we move in the direction as defined by the data that we receive from the event. So the player takes these two pieces of information, just start or stop and left or right, and converts that into actionable data internally, but whoever is providing a move command doesn't care about where that's coming from, right? So this could be implemented as keyboard input, which is what we have. So we have our keyboard input here, which is set up in Unity. It's a script that sits there and it has the left and right keys. So the paddle doesn't care about what keys specifically trigger what movements. And then in update, we check each key and then we move. Now, like I said, Unity's new input system is actually, I believe, event-based. I haven't really worked with it at all, but I do believe it's event-based. And other input systems like Rewired or In Control also have the option to be event-based, and so you receive this kind of input, this kind of event callback already. In our case, we're manually checking an update and then sending an event, but we're checking an update and not the physics update step, which is different in Unity. So there is some level of decoupling there. Not to mention that, again, the player doesn't actually care where the paddle doesn't care where the movement is coming from, and the input doesn't care where the movement is going to. So we check our key, and then if it's down, we dispatch a start in that direction, and if it's up, we dispatch a stop in that direction. So we move left, move right. It's pretty straightforward, and that gives us our input. So the next thing that we have is a brick broken event. So let's go over to our bricks here. So we have brick, and we have simple brick. We provide a Unity event as well on the brick in case we wanted to add any effects, and we'll see that. Actually, I don't think we end up using that, but I'll show you what this looks like in Unity, for example. But we have on collision enter, which interestingly, this method, if you're somebody who's been working with Unity and you've worked with the physics system, you know that you can just basically put like magic methods in your mono behaviors and things will get called. These are actually just events. And in this case, like it says right here in Writer, it actually tells me, hey, this is a Unity event function. And so Unity actually uses this pattern for their physics system naturally to decouple physics from the actual implementation. That really makes sense for when you're writing a game engine, right? But in any case, we have we check, if what we collided with is a ball, then we break, and we provide the ball as a parameter because we are going to dispatch an event that we've been broken, and we say, we as the source, this brick has been broken, and by this ball, right? So we send the ball in with the event. So this ball broke this brick. You have to think about what's the information that you want to encapsulate in this event. This one makes a lot of sense for brick broken. It's the two most important parts. Then we call our Unity event, and then we destroy ourselves. And so we have to do these things before we destroy ourselves because we don't want any weird side effects from us not existing anymore when this stuff is invoked. So finally, we have a ball collided event. And so this is sent whenever a ball collides with something. And it provides the collision event. So we can go over to ball and we'll see that. So ball has some physics stuff. We don't have to worry too much, some initialization. Then we have on collision enter with something else. Then we immediately pass that along to our event system. And we say, hey, I as a ball collided with something else. So we let everybody else know that we collided with something. That's pretty much the core stuff for this game to work, right? But we're not really doing anything with these events. We're sending them. We are doing a little bit with the input, but we're not doing a lot else. So we'll get into that. And we'll start at the input. So we have keyboard input, and that's cool. But I mentioned that you can have other kinds of input. Like, let's say, for example, we wanted to port this game to mobile. And so we thought, well, we'll just do the lazy thing and add some on-screen controls. And so we'll just have some buttons on screen that you can press to move right and left. And to implement this, I didn't have to call player.moveLeft, player.moveRight in these buttons, nor did I have to make the player aware of the UI, because that would be ridiculously backwards. But instead, I implemented a UI input button here. And unfortunately, there's a little bit kind of complex to listen for mouse down and mouse up events on buttons, which we need to start and stop. So we can kind of ignore everything here. But jumping down to these two calls, this is really an important part. So when our button is pressed down, that's that pointer down event trigger type, we dispatch a move event start in our direction. So this is defined as this mono behavior has a direction that is assigned in the Unity editor. So when we go to Unity, we can see, let's see here. We have our left and right buttons, and we can see the input button. Well, unfortunately, I changed it to be integers, so unfortunately it's no longer assignable. But if I hadn't messed with things last minute, it would be assignable in the Unity editor. Unfortunately, there's some funky serialization stuff that happens with Unity. Oh, I see. No, this is the problem. There we go. Okay, should be good now. Okay, yeah, so you can see left and right available here. I'm very quick to blame Unity serialization system. This is a recurring theme. Yeah, and so actually also interestingly, again, with the UI stuff, we're using events. Again, this is another common place where, especially in engines, it's really great to just automatically use the observer pattern. So Unity under the hood has some kind of observer-like implementation for listening to UI button events to then turn them into something in your game. So that's a quick way to implement some like additional controls. And interestingly as well, the keyboard controls still work on top of these UI controls because it sends new events when I press this, right? So I can use these on-screen controls, but I can also use the keyboard because they don't care about each other. They don't have to know about each other. We could also, of course, interestingly, like I mentioned earlier, we could implement a simple AI using the exact same system. So the AI now just uses the input system that we've already set up with events and manipulates the paddle itself. And so in this case, the AI effectively just watches the ball and dispatches move events to try to follow the ball. And it's maybe not the best AI, or at least it is too good of an AI. But suddenly we have an autoplay feature, for example, super easily, right? Again, basically no change to the paddle code to add this kind of feature. And I can, like you just saw, I ran the game and then I turned on this thing and then it enables it. So it's easy to enable and disable these systems on the fly. Like I said, these are very modular, very easy to change. So I can turn it on, and then I can say, oh, no, actually, I want to take back control. So I'll turn it off, and then I'll take control, right? And we'll turn it back on, we turn it off, and then, now we have control. So that's I think, really strong. Input is a great use for the observer pattern or for event-based architecture in general. The next thing that we can do, of course, it's hard for me to do any talk without talking about Juice a bit, so we're going to spend a bit of time on that. And to be fair, I think it's really important for rapid prototyping because a lot of the process when you get kind of later in a prototype is to juice it for stakeholders to convince either whether it's players at playtesting, so you want to make it look a little bit better, to get less art-focused feedback and try to get more gameplay-focused feedback, or if it is for a Kickstarter or for selling to some other kind of stakeholder, you probably want it to be as easy as possible to quickly kick up the juice level in the game. So it's super simple to just add some effects. So for example, we can set up some dust of particles to play when the ball collides with things. We have that ball collision event. We can go ahead and listen to that. So we'll go ahead and let our AI play here. And so what we can do is we could maybe say, okay, well, let's have some dust pop out of the ball whenever it collides with something. And so now we'll just enable this system. You can see whenever there's a collision, there's a little bit of particle effects. And interestingly, the ball doesn't actually have any you know, you might add a particle system to the ball in Unity and then emit whenever the ball collides on something, so the ball knows about its particles. There's coupling there, right? The particles system is now coupled to the ball, or at least in this specific instance, the ball's visual representation is coupled. So we're not doing that though, right? The ball still just emits these collision events. It does nothing different. The only thing that's different is now there's somebody listening for them. And all that this script does is, let's go ahead and stop this back here. All that this script does is listens for that ball collided event and gets a particle effect from a pool that we have here. So we have a pool of particle effects. And on collision, on the collision event, gets the collision information, gets the particle system, and sets the position and rotation to match the information that we have from the collision information, and plays the effect. It's that simple. Move to where it happened, set ourselves up, fire and forget, right? So a quick and simple response. And we don't have to do any of this from the ball. The ball, again, remains just a simple, kind of manages its own physics, and that's about it. It notifies when it's collided with something, right? The ball doesn't even know that there's bricks in this game. So we could also add some screen shake, a classic juice effect, right? So we have our dust. We might also choose to add some screen shake. So we could, in Unity, we have Cinemachine, so we're going to use that to do the screen shake. And Cinemachine has its own impulse listener. Literally, it's in the name. This is using the observer pattern. So this listens for impulses, which are a kind of event in Cinemachine that tells the camera to shake. And so in this case, on the ball, we've attached a component that dispatches it's called an impulse source. It dispatches an impulse on collision. So it's very similar to the system that we're using. Now, if you're not using Unity, if you don't have something like this, you have your own bespoke screen shake system, you could listen for that ball collided event. It'd work the same. So now we have, let me turn my AI back on. So now we have, whenever the ball hits something, we get a little bit of wiggle. And again, we get collision information, so we can do things like tilt the camera in the direction that the ball collided, right? So we can kind of bump it in the direction that it collided, and it feels really nice. Now there's already a lot of springiness. And this is, again, basically a low to no code type of situation, especially if you already have some of these systems already set up, if you already have effect pools and these kind of systems that you are reusing from your older projects. You can quickly kind of do this stuff. And even another case for how this is so good for rapid prototyping is we can say, say our designer's like, well, what if there were a lot more balls? What if we had a feature where you could get 3 triple ball, right? And so we have 3 balls going. Well, this system still works the same because the number of balls doesn't matter. The number of sources for these events doesn't really matter. Because everybody's just listening for the event, and so now there's just 3 more cases, or 2 more cases where the event can be dispatched, so it still all works the same. No additional code. So you can quickly make changes to your game. I mean, I can put a bunch more balls in, and it goes crazy, right? It still works, though. And even when the balls collide with each other, there's a little bit of particles, because it's state independent, right? It doesn't care about who or what. It just knows that there was a collision of a ball. So this is pretty hog wild, but that's a really simple example of how this can quickly scale into something that's like, okay, your designer comes to you and has a feature, and you're like, oh well, that's actually not so hard. Give me an hour, right? And that's where that rapid prototyping comes in. So we can do the same thing for bricks exploding with the brick break effect. It's pretty much the exact same code. You can see now we have a little effect that plays when bricks break, and we can even get the color from the brick because we have the brick in the event, so we can use that information to color our effect, even though it's coming from a pool of effects, so they're independent of the bricks. Because again, bricks are just simple objects. They just have a collider and the brick script and a renderer for the sprite. So we can use that color and update the effect there. and then play it. So now let's say your designer comes to you and says, well, this game is cool and all, you can't lose, but that's hot these days, so we'll keep that. And what else is hot is giving points to players and giving them some kind of reward, right? People really love that. I know that's like new to the game scene. I don't know if you guys have heard about it, but points are pretty cool. So your designer comes to you and says, let's add some points. And so we can say, well, when a brick breaks, let's just give the player 50 points, let's say. And you might say, okay, well, we'll give the brick a value of 50, and then when the brick is broken, in the brick we'll go, probably have a score global value somewhere, and you increment that. Or God forbid you have a reference to the player and you say player.score plus 50, right? Like, you could do that. But what if we kept these systems separate and decoupled, and instead, let's say we have a score manager that has the brick value encapsulated within it. It is separation of concerns. The brick shouldn't be so much concerned about its own value. The score manager is what assigns value. Or the score system, right? And so we have score manager that holds a value and it knows what the current score is. And on awake, it listens for a brick broken event, which again, we've established we already have. So this is no new code yet. And then in that listener, we say, okay, well, we're going to award the player the brick value because this is a brick broken event. And we'll add the award to our score, and then we'll dispatch a points awarded event. Now, again, we could do a points changed event here, and I would encourage, and there's in the references some kind of further reading, I would encourage maybe looking into that pattern. I just didn't, it's a little bit out of the scope of this talk, and we'll touch on it very slightly at the end, but you could also just do when the value changes, dispatch an event. But in this case, points awarded. And we say in the points awarded event, we say that we have the award, we have the current score, so we have how much was awarded, what the score is, and then we have this transform source. So in this case, the data that we're concerned with is where the score came from, and that'll come into play for our next little segment. But we have the score manager, so let's go ahead and bring that in. So we'll add our score manager here, right? And we say the brick value is 50, and then we can go and in our game, well, congratulations. Oh, I've left the effect on. Now I've spoiled I've spoiled the future. Oh well. So we can go in and we can run. Congratulations, maybe points are being awarded. We're probably going to need some kind of UI. So we'll bring in some kind of score display, UI, right, that updates whenever the score is awarded. And we've already kind of covered this example at the top in the presentation, but just for a recap, we have text and we listen for an event and we update the text based on the data from the event. It's that simple. So we have scores being displayed on screen. Maybe we also want to show, your designer comes and says, oh, this just isn't enough feedback. We really need to juice it up. The player really needs to feel satisfied every time a brick breaks, and they need to know that they really earned something. There's not enough tight correlation between the score and the bricks, and we just want to increase that a little bit. And you go, okay, well, they say, well, we want to have some kind of display to let some feedback to let the player know that they earned points. And we say, okay, well, I already have this event. I already know how much was earned. I can just spawn another effect where the brick was broken. That's that transform source. And we can show the points awarded. And so now you see, oh yeah, I earned 50. Now that looks nice. And again, this is fully decoupled from the score manager. The score manager doesn't care about the stuff being displayed on the screen. So it doesn't know about these pop-ups. These pop-ups don't even really know about the score manager. They just know that points were awarded somewhere and they put an effect in that place. It's that simple. So again, it's really easy to change. So let me turn some of that stuff on. Actually, we'll go ahead and jump ahead just to be sure that I didn't. Okay, so we've jumped ourselves forward a bit. What's that? Right, that's fine, we'll leave that. So just to make sure that we have all of these fancy features that we walked through, just so I didn't forget anything. Yep, so we've got our points being awarded, we got pop-ups. Okay, so as a final example, let's say your designer comes to you exasperated and says, the players still don't feel like we still don't feel like there's enough for them here. We want to add a new feature. Hopefully it doesn't take too long because I know we're running out of budget. So we want to add a combo to this game. So whenever a brick is broken, for every brick that's broken, before the ball touches the paddle again, we want the combo to be increased. And so we want a combo reward for every brick broken in sequence, right? So first one 50, next one 100, 150, so on. You say, well, first of all, you tell your PM that it will take you 4 hours or a day or whatever, way more than you think you need. And then you go and spend 20 minutes writing a little extension to, well, 20 minutes if you haven't prepared. You spend about 5 minutes if you have prepared, writing an extension to your score manager, because again, separation of concerns, we don't care about brick broken event. So what we're going to do is multiply the points awarded for each brick broken between paddle hits, and really all we have to do there is we say, we'll add a little combo counter, and we'll be good boys and not have magic numbers. So we'll define that as combo base. So we'll keep track of our combo in Score Manager, and then every time that a brick is broken, we will increment the combo, and multiply the award by the combo. Okay, easy enough, but that only gets us so far. We only have 1/2 of our requirement here. So yes, every time a brick is broken, we earn more combo, but there's no reset when the paddle's hit. Well, conveniently, we also have a ball collided event. So we're gonna go ahead and just add another event listener real quick. Ball collided event. Ooh. And we'll go ahead and create the listener method for that. Ooh, I am missing a brace. There we go, or a bracket. There we are. And we'll move that down. Just as convention, I like to keep my event listeners at the bottom of my class. And of course, we will add a remove, because you always want to remove your listeners. And again, we'll touch on exactly why, but you really do always want to do that. So remove our listener at the end. And now we have our listener here. It gets called whenever a ball collides. We'll call it E. And we'll say if the combo is not the base value and the collision use transform dot tag compare tag. So if it is the paddle, so if we collided with the paddle, then reset combo. So if we're not already at the base and we collided with the paddle, then we reset combo. And now, if we play, we should see, so we earned 50 there, but this time we'll earn 100, 150, 200, look at that. And did you notice that our display also updates because it doesn't care about the combo, it just cares about points awarded, and we're awarding more points, and so it's going to display the increased award. Again, these systems, if considered a little bit, and then as you start to use this pattern and get more familiar with it, these things start to dovetail really nicely, and just small changes can quickly add up. So we have that, but then your designer comes back to you and says, well, the players are confused now because they don't know why they earn different points at different times. So you say, okay, and they say, how long would it take to implement a combo display in the UI so that they know what combo they have at all times? And you think, oh, that'll probably take about 5 minutes. So you tell your PM 2 hours. And then you go into Unity, and we can just quickly, let's see, we have our score here. Just go ahead and create a separate little combo area. So we'll say, ooh, that's a little small. There we go. So we'll just attach that there, and we will just make it a little bit fancy. And that should be good. And so we'll really do pretty much the exact same thing we're doing with the scoreboard. And so much so that I'm actually just going to copy and paste it. Forgive my sins a little bit, but so we'll say UI combo, and in UI combo, we will listen, instead of for reports awarded event, we will listen for a new event called combo changed event. Hey, look at that. We're gonna do a changed event. So this is a value changed event. So we'll say, really all we care about is the value. So we provide the constructor that assigns the value, and then we provide access for that. So now we'll implement that. And we will say, please, we'll just go ahead and define this ourselves. Great, and of course, oh wait, I should have this. Oh, there we go. And then of course remove it. We'll initialize our text to 1. In an ideal world, we might fire a combo change straight at the start or something like that. But we'll go ahead and initialize that the same way we were doing the other one. And now here's the meat and potatoes. We say text equals e.value.toString. Oh, actually, we want to add that little x. So we'll say value. There we go. So when combo changed, we'll set the text to x and then value of the combo value. And now in our score manager, the last thing is we just need to emit this from somewhere. And where we'll do that is just where we change combo. So here, event dispatcher, dispatch, new combo changed event, combo. And we'll put that down here. Now you see I did just have to copy and paste, and that's, you may or may not know that the general rule of thumb is if you have to copy and paste code, you might want to think about how you could make that, that system better, right? And so in this case, what we could do is actually define a property with getter that just returns the combo and a setter that says combo equals value, and then we dispatch our event here with the new value. And so it does assignment and dispatches the event. And this is kind of the seed of the more advanced pattern, which is defined in a Unite talk that I link, which basically kind of explains how you can get even crazier with decoupling and this kind of pattern, among other things. But basically just having your values have a setter that as a side effect just dispatches an event is really kind of powerful. Just of course we'll need to remember to use that property, and we'll remove this. Okay, great. I think we're using it everywhere. Great. So now we should be able to go back to our game here and add a UI combo element, and let's see what happens. pardon the Unity error here. It's just an editor error. There you go. You see our combo. That was a really powerful one. Usually don't get that good of stuff. So you have our combo here, and it works pretty well. It increments with, I think I anchored it wrong, so it moved a little bit funny, but it increments with each combo. It shows what your current combo is, and then it resets when it's done, or when it resets at the paddle. And of course, as with before, your designer says, well, we need more balls in the game, because every game needs more things flying around on screen. And this still works more or less the same. It's our designer's fault for not saying that it had to be one specific ball, but if any ball touches the paddle, then it resets the combo. So in this case, we have a global combo that resets whenever any ball, that increments whenever any ball breaks a brick, and resets when any ball touches the paddle. But it works, and it, again, no code to just throw in a bunch of extra balls, and then it works. There's no coupling here. There's not, a weird situation where you can't, if you add one more ball, then it doesn't get added to some other system, and then it's not being paid attention to by the score manager or whatever. Like, the events help decouple all of that stuff. And so it's really quick to plug and play, right? You can pull out systems, put in new systems. Especially with some intelligent design, you can really get pretty fancy with how reusable and modular stuff is. And testable, because you can fire events from like a test script and say like, hey, just fire this event when I press a button so that I can see if this thing works, right? So that's the core of it. I did promise, just as a really tiny sidebar, I want to get moving because I know we're getting close to time and there's a little bit more presentation left. But as a quick sidebar, I did promise I would show what the Unity event looks like in the editor. Here it is. You can add things that receive callbacks for the event. So we could say, set our name to something when we break, which would be weird. But you see, you can assign this to anything. And you'll have different editor references, which can create some scary stuff. But especially for like one-off particle effects or stuff that's local to the prefab, it's not an uncommon pattern for me at all to put the particle under the prefab and fire it through a Unity event, because it's all encapsulated in one object, and so it's not very easy to break references. Cool. Yeah, so that's kind of the basis of it, right? Again, this is all available on GitHub in the demo repo, so you can pull that whole thing down, crack it open in Unity, poke around with this a little bit more detail if you'd like. Great, so let's go back to our presentation. So finally, let's talk about gotchas. So no pattern is a silver bullet. This one, in my opinion, is very near to a silver bullet in a lot of cases, especially when it comes to game development. But no pattern is a silver bullet. The core big problems that you encounter with this pattern primarily are the issue of lapsed listeners, which is what I was kind of hinting at earlier. Invocation order, which you may not have considered yet, but what order are those events actually called in, right? Or those callbacks called in. Debugging can be a little tricky, and there may be some performance concerns. Let's walk through it. Lapse listeners. Lapse listeners are basically a listener that is registered but not removed when it should be. So it's added to the subject, and it listens for events, but then when the parent class or whatever, when the subject is destroyed, or when the instance is dereferenced, the listener is not destroyed, because the subject has a reference to the listener and it's holding on to it, so it remains in memory. And so that becomes a lapse listener. It's now a method with no instance, which in Unity and C# can create some really interesting problems, because that instance is encapsulated with the method as a listener, and so when the instance disappears, you can get null reference errors on this, which is very scary. But when you see that, oh, I have a lapsed listener that's being invoked. In Unity, it means listeners persist even if the game object or mono behavior is destroyed, especially between scene changes. That can happen. So you think like, this game's working great, and then you reload the scene and you get a bunch of references that say this is null, and you're like, that can't be possible. Well, it can actually. Lapse listeners, yeah, they're still called. So that can lead to, like I said, the null reference, duplicated or unexpected behavior because more than one of the same method is being called. You might notice this with particle systems or audio. We had a bug in a game where audio effects got doubled up every scene reload. That sucked. And it can create memory leaks because things remain in memory when they shouldn't, even if they don't have any overt effect. So always be sure to remove your listeners when they should be. Consider the life cycle. There's some cases where the listener will be there forever because it'll be there for the full life cycle of the application. That's great. Just be careful there. Remove your listeners. In Unity, it's as simple as putting a remove call in onDestroy. In this case, we can also keep track of the listeners that we've registered to automatically remove them. So in onDestroy, we call remove all listeners, and it walks through a list of listeners that we've added and removes them. If that's something that interests you, it adds a little bit more overhead, but it is, especially for rapid prototyping, a lot easier to just on the fly be like, just start listening. I don't care. It'll work later. It's a little bit safer. It's also a little bit lazier. You allocate, you keep track of your listeners in a list there, but the overhead is very, very minor. And I think that for the benefit, this is something that we use internally often. Just quickly add it and just forget about it. We've started using that a lot in our most recent prototype because it's just easier when you're rapid prototyping. You want to reduce friction as much as possible. So we just say add listener and then do the thing. We don't even have to worry. It's going to get called later. But we have to, of course, in this case, we're extending mono behavior, and then we have our custom behavior that extends it. Invocation order. Invocation order is not necessarily deterministic. So the order in which the things are called doesn't necessarily correlate to anything. Listeners may be registered and removed at different times throughout the application's lifecycle. So you don't, even if you had an idea of what order things were being called, that could change at any time, and you really shouldn't rely on that. In C#, event listeners are technically called in the same order as they are registered, but this is not defined behavior in the spec for C#, so it could change at any time. Probably won't, but you shouldn't program against undefined behavior. That's not, you're asking for problems in that case. And more importantly, if your listeners need to be called in a specific order, that's a serious red flag that you're misusing the design pattern. Plain and simple. Debugging. So logic flow can be harder to follow with events versus direct calls. It can be harder to, especially if you're not familiar with working with events, to figure out, what order things are happening or like why things are happening in general. You just see like an event being fired and you're like, well, I don't know what's going on. And it's harder to trace like when is an event being fired or where is the control coming from. Control flow is just really, really difficult. Modern IDEs can help with this. So a lot of Visual Studio, I assume MonoDevelop, Writer, all of them have some kind of way to find usages of a type or usages of references to a type. And so with our system, you could just say, everywhere that this event is used, show me that, and then I'll step through and try to find like, okay, well, this is a listener, so on and so forth. Like I said, it comes with time and experience. And thanks to modularity, you can also break out and test parts of your system in isolation if you still can't figure it out and you're trying to debug. So there's a boon there as well. So it's a little bit of both. And again, I think with time and experience, it honestly really does get better. I didn't know there's an animation. I kind of forgot there was an image on this slide. But this has been me. So there might be some people here that are thinking, well, like, what about performance, right? Like that's got to be a concern in the system. There's all these objects, this, deferred calls. That seems like it would really be a damper on your performance. Robert Nystrom has a really good way of putting this. Sending a notification is simply walking a list and calling some virtual methods. Granted, it's a bit slower than a statically dispatched call, i.e., a direct call, but that cost is negligible in all but the most performance-critical code. He goes on to say that I find this pattern fits best outside of the hot code paths anyways, so you can usually afford the dynamic dispatch. Aside from that, there's virtually no overhead. So the cost is negligible in all but the most performance-critical code, and there's virtually no overhead. And it's true. you should probably try to avoid, sending events every frame, lots of events every frame. But even so, that cost isn't so great. And honestly, we don't need to worry about performance too much when we're rapid prototyping, right? We just want to get to the thing. But you can try to keep your observers from blocking the rest of the invocation for too long. So try to keep what they do in the observer pretty snappy. Don't wait for the results from some API or something weird. Offload work, or don't load from the file system. Offload work from the observer method if necessary. So send that off somewhere else if you need to. Defer it to the next frame or across multiple frames or whatever you need to do into another thread if you're working in a multi-threaded kind of environment. And don't worry too much about performance, especially for rapid prototyping. Events can be optimized or refactored away in the future. That's the nice thing about them being so modular and so open for modification. And right now, if we're rapid prototyping and that's what we're focused on, we care more about that modularity, testability, and reusability. And the affordances provided by those way outweigh the tiny, tiny performance difference. And as a sidebar, and I'll try to be really quick because I'm getting low on time here, the Unity event and C# event performance. This is something that was brought to my attention by a friend of mine, Rowan Waring, and also Rock Game Dev community member. So C# event invocation is always faster than Unity events, and adding listeners to C# events may create marginally more garbage allocation than Unity events. It depends on the Unity version and the .NET version. There's a blog post that Rowan sent to me that's quite outdated and actually has changed a bit, and I did some tests to show that. So this is from the original blog post. Basically, invocation performance scales. The C# events are always faster. This is across, it was like millions of invocations in, that's why the milliseconds is so high. You might be seeing, 200 milliseconds and screaming. That's because it was millions of invocations. But you can see it scales linearly with the number of listeners and also somewhat with the number of arguments, right? But the point here is that the Unity events do take longer to invoke, but again, this is across millions of calls. The amount of cost in one frame for a game in a real application is basically none. The difference is so negligible, the size difference, or the marginal difference here. Now, garbage allocation for managed, since C# is a managed language, the C# events, as you add listeners, does allocate more garbage. This is what in Unity 5.3, which is what this person used in this blog, this is, it scales actually quite alarmingly, you might think. After the fourth, you're getting, not too much, but, like 1.2 kilobytes is not anything to shake a stick at either, especially in games. But to be fair, in newer versions of .NET, this actually is reduced, and this is my own test that I ran in Unity 2020. The gap is much smaller. Still, we kind of get up there as we add more and more listeners, but really, events often don't have a lot of listeners too often. You usually don't exceed 2 or 3. Plus, well, the takeaway here is that event invocation, C# event invocation, is always faster than a Unity event. Adding listeners to C# events may create marginally more garbage, but it depends on the .NET version. Garbage can be manually collected after startup registration, which minimizes the impact on player experience. So you can collect your garbage. You can do all of your event registration in the first frame, collect garbage, and then move on to doing the game or during loading or whatever, right? And listeners are most often added right at the start or at a wake on an object or something. They're really only added once. They're not added and removed very frequently. Something that you should avoid, but don't necessarily shy too far away from. Again, remember this is rapid prototyping. We don't care so much about garbage right now. Just kind of try to avoid adding or removing listeners frequently if you're concerned about garbage being created. Prefer Unity event when you want the editor features that the Unity event has. Otherwise, prefer C# events because they're always better. The garbage difference is really marginal and can be mitigated. But you might be saying, like, but the performance is different. It's bad. You don't need to over-optimize, and you should really be wary of it. It's a trap that I've fallen into, and I've seen lots of friends fall into. Especially for rapid prototyping, you're wasting your time, really. You're probably going to throw away this project. You're probably not going to, it's probably going to change significantly. And so if you spend time optimizing, you're kind of, you're really concerning yourself with the wrong problems. So if you find yourself feeling this way during rapid prototyping, unless you're having serious issues, just look at this image. The final thing the secret fifth problem is overuse. Like I said at the top, with singletons, once you have a hammer, everything's a nail. The same can absolutely apply to events, and so you have to be careful not to kind of go too wild with like just making everything an event, and it all communicates through some kind of abstract structure where data is just being thrown around left and right. Robert Nystrom actually provides a really good rule of thumb for this, which is if you often need to think about both sides of some communication in order to understand a part of the program, don't use the observer pattern to express that linkage. Prefer something more explicit. So when you have to think about both sides of the communication to make the system work, then the observer pattern probably doesn't apply. It's more of a one-way notification, receive notification. He goes on to say that we want the bare minimum of communication between the subject and the observer so that working on either one doesn't require much knowledge of the other. So again, keep that as a rule of thumb. You really want the bare minimum of communication. And you really don't want, there are some cases, but you want to try to avoid two-way communication. So to avoid just slapping everything into an event and annoying everybody else on your team because it's now impossible to debug or understand what's happening in your program, consider these rules of thumb. So additional resources here. Like I said, W3S Design, they cover all sorts of Gang of 4 patterns and break it down in a way that I found was really digestible. So that's really cool. Game Programming Patterns is, again, an incredible resource. They have a whole subject on, or a whole chapter on the observer pattern, which I think is great. But there's lots of other awesome patterns in there, and I might, even in the future do talks on that because there's lots of other really interesting things in there. For the C# Unity folks in the crowd, you can check out the event performance blog I mentioned. Like I said, it's a little bit outdated and the information's not totally correct, so don't go telling everybody that the garbage creation is exponential. And this Unite Austin talk, which talks about, it's called Game Architecture with Scriptable Objects. It's got a lot of Unity-specific decoupling patterns in it that go well beyond just the observer pattern, but it does touch on the observer pattern in a unique way of wiring up events and listeners in a kind of codeless or code minimal way, which I think is really cool, and it was way outside of the scope of this talk, but I want to explore that more in the future. And then of course there's a link to the GitHub repo. I did include the event dispatcher. If you are a C# Unity person, please feel free to plunder. That's all MIT licensed, so plunder away from that repo. Please feel free to take that code and modify it and make it work for you and your situation. I'm happy to share that kind of stuff. I hope that it is helpful. So with that, that's been whatever long title I gave to this talk. Oh, it's right over here. Prototype Faster with Event-Based Architecture. I've been Noah Ratcliff. You can reach me on Twitter at 20c109. You can email me, noah@aesthetic.games. Please let me know if you have any questions. DMs are open on Twitter. My inbox is open. And you can check out the work that we're doing as a team at aesthetic.games. And like I said, please feel free to reach out with any questions, or if you have any in the chat, hit me up. I'll hang out here for a little bit while you furiously pound your keyboards over there. And yeah, thanks again.